deep dive a little bit to understand how data is actually stored in the computer. Bit is the smallest storage possible in computers. A bit is like a light bulb. It can either be turned on or turned off. A bit can be either a 0 or a 1. If we take 8 bits together, the combination of 8 bits is called a byte. A byte gives us some more options of turning up to 8 bits on or off. Byte is the smallest storage that is meaningful for us for storing numbers and strings, and you will soon see. If we take 1 byte with all 8 bits turned off, we define that to represent the number 0. If we turn on only 1 bit on, the rightmost bit, we define that to represent the number 1. If we turn on just the second bit from the right, we define that byte to represent the number 2. Are you thinking about the number 3? Do you have any guess? Well, we already know how we define 0, 1, and 2 to be represented by byte. Let's see how this has been defined, actually. We assign each bit a number. The rightmost bit is assigned the number 1. The second bit from the right is assigned the number 2. The third bit is assigned the number 4, and so on and so forth. You can see there is a pattern here. 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, 4 multiplied by 2 is 8, etc., etc. Actually, since each bit has only 2 options, this pattern is received by taking the power of 2. So 2 to the power of 0 gives us 1, 2 to the power of 1 gives us 2, 2 to the power of 2 gives us 4, etc., etc. We can say that up to the third position, if we only look to the right at the 2 first bits, we have up to 2 by 2 possible combinations of these 2 bytes. These 2 can either be both turned off, can either be turned on, and either one can be turned on while the other is off. We therefore have 4 possible combinations, and that's why the third bit is represented by the number 4. If we take the 3 bits, how many combinations do we have for 3 bits now? Well, it turns out we have 8 possible combinations. Take a sheet of paper and try it out. So these are the rules that define our pattern for representing numbers within a byte. So if we follow this rule, the number 3 is now represented by turning on bit number 1 and bit number 2. Bit number 1 represents the number 1. Bit number 2 represents the number 2. We added those 2 together and we get a 3. The number 4 will be represented by just turning on the third bit, because number 4 is representing the third bit. Using the same logic, how do we represent the number 26? We turn on the bit that is represented by 16, then we turn on the bit that is represented by the number 8. 16 plus 8, that gives us 24, so we're missing 2. We have the second bit that is represented by the number 2 to add on to that, So these three specific bits come together to represent the number 26. Now, if we turn all 8 bits, what do we get? We need to add 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. That brings us to 255. So the largest possible number, whole number, that we can represent using a single byte is 255. So how do we represent larger numbers? How do we represent 256? How do we represent 2008? Well, we do that by concatenating 2 bytes together. In this way, we have extended the 8 bits available within 1 byte into 16 bits that now allows us a combination of 16 possible ones and zeros along those 2 bytes, whereas the 16th bit represents the 65,536. So you can imagine that many combinations are possible with 16 bits. However, we must consider representing also negative numbers. For that, we sacrifice the most significant bit, which is the leftmost bit here, to represent the negative sign in case we are representing signed numbers as opposed to unsigned numbers. So with unsigned numbers, we use all of the bits available to represent positive numbers only. With signed numbers, we represent both negative and positive numbers by using the leftmost or most significant bit along with 2 complements of the rest of the bits. Let me show you what I mean. This is the regular representation of 266. We're taking 256, we're adding 8, and we're adding 2. That brings us to 266. Now, in order to do the trick to represent the negative 266, we first take the 266 representation and apply the first complement to it, which is basically just toggling all of its bits. So every bit that was 0 now becomes 1, and every bit that was 1 now becomes 0. This is 266 first complement. Then we do the second complement on that representation, which is basically adding 1 to the ones complement. Adding 1 in binary means that we are running from the right, from the least significant digit, from the right to the left, the direction, on a representation. And whenever we encounter the first 0, we stop, and then we flip, we toggle all of the bits that we encountered so far. So in our example, we start with the first bit, which is 1. Since it's not 0, we are continuing to the next bit from right to left, which is 0. So now we've encountered our first 0. So what we do now is that we flip that 0 to 1 and the previous 1 to 0. So as you can see, these 2 bits were flipped back to what they were originally by just adding 1 to the ones complement. And our leftmost bit is turned on, which tells us that this represents a negative number. So this way we tell our computer that this is a negative number in case we have defined for the compiler that this is a signed number. So this bit is used to represent the negative number if it is 1, and that it must be decomplemented back to this representation of 266 together with the minus sign that is represented by this bit. So this is how we would represent minus 266. So we know how we can represent numbers. How about characters, strings? What we can do is decide that each character is represented by a numeric code. Now, since we already know how to represent and store numbers, we can store strings by storing many, many numbers one after the other. For that, we have an ASCII table, ASCII. That is the very first table that was defined in the first days of computers to represent the alphabetical set of strings, of characters. Now, an ASCII table has only 1 byte to represent characters. And we know that 1 byte is very limiting. We can store up to 255 numbers or 128 characters if we omit the leftmost bit. But the ASCII table is still very popular, and it represents all of the characters in the English alphabet and some other characters as well. For example, the letter A in capital is represented by the number 65. The letter B in capital is represented by the number 66. The space character is represented by 32. The double quote is represented by 34. The number 3 as a string, as a character, not as a number, is represented by code 51. But how do we represent all other languages? For that, the Unicode method was developed. The Unicode table can be very, very long. There's no longer a limit of the number of bytes to represent characters. You can decide how many characters you want to add together to represent whatever character you need. So the Unicode table actually can hold tens of thousands of characters, 120,000 characters. All of the world languages and other symbols are included and represented by the Unicode method.